Recall that the first law of thermodynamics states that energy cannot be created or destroyed. The energy of the universe is constant. So energy that is lost by a system is going to exactly equal energy absorbed by the surroundings. We can show, as we've discussed, energy being lost as a negative value. It's of course not negative energy, it's just showing that it's leaving the system, and so the total energy of the system goes down. Energy being absorbed is positive value because the total energy would go up. I'm going to rewrite this to match what it says up there. So energy lost by the system, so negative Q of the system, equals the energy absorbed by the surroundings. So the energy lost by the system equals the energy absorbed by the surroundings. Because Q equals Sm delta T, we can then substitute Sm delta T into that Q, negative Q system equals positive Q surroundings, and get our second formula, our third formula of this chapter, S1 M1 delta T1 equals negative S2 M2 delta T2. When using this formula, it's pretty much the same as just using the Q equals Sm delta T. You just use everything twice. You will recognize these problems because there's a lot more variables involved and because you have two substances. What we were doing before was just, I'm heating a piece of iron or I'm cooling water. Now we have a 125 gram sample of iron. So we have iron at 93 is dropped into an unknown mass of water at 25. Final temperature of the mixture is 32. I'm going to calculate the mass of the water. That's another M. Of course, specific heats are constant values. So the specific heat of iron is 0.45, and specific heat of water is 4.184 joules per gram degree Celsius. Those are constant values. I didn't do anything to get those numbers. You can get them off a table, or oftentimes I will actually include them in the problem. So these are both S's. So I have two M's, two S's, a bunch of T's. When I'm setting this up, it's a good idea to kind of separate it so that you can keep track and have an S, an M, and a delta T for both the iron and the water. So specific heat of iron is 0.45, specific heat of water 4.184, mass of iron 125, mass of water is what I'm solving for, delta T. So as you learned a couple days ago, hot things transfer energy to cold things until they are the same temperature. It's called thermal equilibrium. And so the final temperature of the mixture is 32 degrees Celsius, which means that both the iron and the water end up at 32 degrees Celsius. So when I'm calculating my delta T and I'm doing final minus initial, the final for both is 32. The iron started at 93.5. The water started at 25. So the iron's going to decrease 61.5 degrees. The water is going to increase 7 degrees. Huge difference there. That difference is because of the difference in specific heats. Once you have all that set up, you just go ahead and plug into the formula. So S1, M1, delta T1 equals negative. That negative is just indicating that the energy is going the other way. So equals negative 4.184 times X times 7. Don't forget that negative, otherwise you're going to get a weird answer like a negative mass or something of that nature. So when I solve this mathematically, I'm going to get that my mass is 118 grams. We talked about thermodynamics before. Now we're going to look specifically at thermochemistry. Thermochemistry is the study of energy changes associated with chemical reactions, specifically with chemical reactions. So enthalpy, whose symbol is H, is an energy function. The enthalpy, the energy content of a system, cannot be measured. You can only measure changes in enthalpy. So you won't be solving for H, you'll be solving for delta H. Okay, delta H is equal, delta H is equal to the energy that flows as heat. So delta H is more or less equivalent to Q. They are not equal. You can't substitute in S1N1 delta T1 for delta H, but they are basically the same thing for our purposes. So when you are using thermochemistry, there's going to be a chemical reaction involved. So I have 1 mole of methane being burned. So that's a combustion reaction, if you recall from a long time ago when we did that. Combustion reactions use oxygen and always produce carbon dioxide and water. And when I go to balance this, I need a 2 in front of the oxygen and a 2 in front of the water. So 1 mole of methane is burned at constant pressure. 890 kilojoules of energy is released as heat. So 1 mole of CH4 is going to release 890 kilojoules of energy. We're going to calculate delta H for a process where 5.8 grams of a sample of methane is burned. So 1 mole releases 890 kilojoules. I don't have a mole, I have 5.8 grams. So we just do a little conversion from grams to moles. So methane 16.05 grams from the periodic table. I can then actually use that as a conversion factor. 1 mole of methane releases 890 kilojoules of energy. So doing that math, you'll get negative 321 kilojoules. You can only use 2 sig figs because of the 5.8 is 2 sig figs, so negative 320 kilojoules is your answer. So this is one way you might see these problems. Alternatively, instead of saying when 1 mole is burned, 890 kilojoules of energy is released, there's 2 other ways I can show this. I can either do adding 890 kilojoules as a product because it's being released, or I can actually just give you delta H equals negative 890 kilojoules. But those all mean the same thing. It means when this reaction occurs, 890 kilojoules of energy is released as heat.